Alrighty, welcome to the first video of Chapter 6, first official video. This is 6.1, Graphing Systems of Equations. So we're going to go through a couple of new important vocabulary words in this section, so I apologize that this one is a little heavy slide, but future sections won't have too much vocab. So here we go, get started. I wanted to mention, for these videos, actually you should watch the whole slide and observe and listen and pay attention first, and then pause and write stuff down, rather than pause and writing stuff down first and then listening. So please do that. First thing, system of equations. What is a system of equations? All this is two or more equations using the same input and output variables. So most often, in a very generic math sense, you'll have y equals some function of x. Okay, you could call this y1 equals f1 of x, and y2 equals f2 of x. So you'll just have two equations. They might be in function notation, they might be in y equals notation, but you'll just have two generic equations that both have x and y in them. And your idea is, when you have these two taken together, they're called a system of equations. Okay, so when it says solve a system of equations or find the solution, what does that mean? So the solution to a system of equations, I'm getting ahead of myself. The solution to a single equation, if you just had one, what would the solution be? Well, any single equation, like y equals 2x plus 5, for example, any point on this line counts as a solution to this equation, because if you plug it in, it's true. So for example, the point 1, 7, if I plug in this point, I put in a 1 for x, 2 times 1 is 2, plus 5 is 7, equals 7. So 7 equals 2 times 1 plus 5. That is true. Therefore, this point is a solution to this equation. But as you can imagine, if you have an equation like y equals 2x plus 5, there's actually an infinite amount of solutions. Every single point on the line is a possible solution. Okay, so now moving on to what I was thinking about before. Solution to a system of equations. So if you have more than one line, how are you possibly a solution to the entire system? The way to be a solution to the whole system is to be a single point that's a solution to all of the individual equations. Okay, so each equation is going to have lots of points on it. However, there's not very many points that are in both lines. So for example, take a look at this graph. The first equation might be this line, x plus y equals 3, which is a line like this. There's an infinite amount of dots all over the place. Every single one of these little dots is a solution to this equation. And then you might have a different equation, this purple line. Every single one of these dots is a solution to the purple line, but there's only one spot that is a solution to both of them. So there's only one solution to this system of equations, and that solution is the point where those two lines cross. Okay? So when you're trying to find the solution to a system of equations, you're looking for the place where they cross, because that single point is simultaneously a solution to both equations because it's on both lines. Okay, so how do we solve for it? Well, there's three things we have to watch out for. A system of equations could have no solution if the two lines are parallel. It could have one solution if the two lines cross. It would be the point where they cross. Or it could have all solutions if it's the same line on top of itself. So imagine you just draw the same line on top of itself. Then they're always crossing, so every single point is a solution. So I'm going to look in a little more detail in Desmos.com at these three possibilities. Okay, so here in Desmos, let's take a look first at two lines that are parallel. So y equals 3x plus 1, and y equals 3x minus 4. So these two lines have the same slopes, and they're parallel. And when you look at them, you can see, even if I zoom out, these two lines are never going to cross, so they would have no solution. This system of equations has no solution. And when we learn some techniques later on to solve it algebraically, you'll get an answer of no solution. Okay, let's look at two lines that cross. So y equals, x plus 2. So here we have two lines that have a different slope, so they're guaranteed to cross, and they cross at exactly one point, which is this point right here. I can zoom in a little bit and make it more obvious. This point right here is 0.5, 2.5. That would be the solution to this system of equations because it's the point where they cross. It's the one single point that's on both of the lines. And lastly, let's look at two lines which are actually the same line. So this is not easy to see, but if I type 2y equals 6x plus 2, it's actually the exact same line. And you didn't even see a difference. You probably just you saw the orange line turn blue when this one came on top of it. But you can tell they're the same because if you divide everything here by 2, divide that by 2, you get y. Divide that by 2, you get 3x. Divide that by 2, you get 1. So it's just the same equation multiplied by 2. But as long as you multiply both sides, then you haven't changed the relationship between x and y, and therefore the graph will be the same. So here the answer would be all solutions. And if you solve it algebraically, like we're going to learn in the future sections, you'll find out that the answer is all solutions that way as well. Alright, so let's come back over here and finish up with the PowerPoint slide. So how do we solve by graphing? The technique is just like I did there with Desmos. You graph both lines together on the same axis, and you just look and see what point it is that they cross. So any point that they cross is a solution. And you can think of this a lot like compound inequalities. If you think back to last chapter, we had a number line, for example, and you might have a compound inequality where we shade this point and we go this way, then we shade this point and we go this way, and the overall answer was just where these two things cross. So with an inequality, it could have been a whole segment of the number line, whereas if it's two lines, it's just going to be a single point. But the idea is the same. Here you had more than one inequality, so the solution was only where they were both true. Here you have more than one line, so again the solution is where they're both true, which is just the point where they cross. Alright, let's use this knowledge to do an example. First one, y equals 2x minus 2. So we have to practice graphing so we get good at graphing quickly. 2x minus 2 starts at negative 2 here, and the slope is positive 2, so I go up 2 over 1, up 2 over 1, up 2 over 1, up 2 over 1, and I'll draw in my line here, like that. That's my first one. My second one, negative 3x minus 5. I'll go down here to negative 5. There's negative 3, 4, 5. And the slope is negative 3x. So down 1, 2, 3, forward 1. Or I could go up 3, back 1, up 3, back 1, up 3, back 1. I can draw this line in. And you can see when you graph these by hand, it's not nearly as nice as when you graph them on Desmos. But I can see that my solution is right here. And so I might have to take a guess, like negative 0.5, the coordinate point, as the x-coordinate, and the y-coordinate negative 1, negative 2, negative 3, maybe negative 3.5. So you can see that while graphing is a great way to visualize it, and a great way to get close, if you don't have the answer at some nice whole number increments, you're actually just going to get a close estimate, but it may be difficult to get the exact value. And that's going to be the reason why in the future sections we learn specific techniques to get the exact value. So if they both start off in y equals form, you can graph them very easily using slope and intercept and get the solution, or at least an approximate solution, by graphing. What happens if the lines start off in standard form or some other form? Well, you need to solve them first into some kind of form that you can graph, or you can graph by finding the intercepts. So I'm going to graph this one by finding the x and y intercepts and see if you guys can remember how to do that. So to find the y-intercept, I set x equal to 0. So imagine this right here is gone. I just have negative y equals 4, so y equals negative 4. That's my y-intercept, negative 4, 1, 2, 3, 4. Plot that point. Now imagine that the y is gone, this is gone. Then I just have 2x equals 4, divide by 2, divide by 2. X equals 2. So x equals 2 is my x-axis. And I can draw a line straight through, as straight as I can, like that. Now for the second one, we'll do the same thing. So we'll find the x-intercept and the y-intercept. So if I set y equal to 0, I'm going to get x equals 5x equals 10. Divide both sides by 5, I'm going to get x equals 2. And now if I set x equal to 0, this is gone. I have 3y equals 10. Divide by 3, divide by 3. Y equals 10 over 3. So I can graph this line again. Y is 10 thirds, which is 3 and 1/3. 1, 2, 3, and 1/3. Here x equals 2 again, so same point. So you can already see they both share that same point. That's obviously the place where they cross. So here's my solution. And here I got it exactly, 2, 0. So I got this solution exactly because I know that both lines go through that specific point. So sometimes you'll get the exact value by graphing. Sometimes you'll only get an approximation if the answer is going to be some nasty decimal. The idea for all of these is to cement in your mind that the point where the two lines cross is the solution, because that one point is simultaneously on both lines. That's absolutely key. And then in future sections we'll learn algebraic techniques on how to solve these and get a precise value. That's it for now. I'll see you next time.